Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to go over an exercise where we're going to apply the intermediate value theorem to the given function f of x squared plus x over x minus 1 over the interval 5 over 2 and 4. And we're going to try to find the value of c guaranteed by the theorem. All right, let's recall the statement of the intermediate value theorem. Let's check the conditions more importantly. So first off, we must have a continuous function defined on a closed interval AB. Okay, that's the first thing. And the second condition is that f must attain different values at the endpoints. Okay, that's good. Number three, so k must be a number between the function values f of a and f of b. So if all three conditions are satisfied, then there exists at least one number, c, so it could be more than one, in the closed interval a, b, such that f attains the value of k at c. Okay, so let's go ahead and check if we can apply the intermediate value theorem. In other words, if we can uh, uh, have the conditions fulfilled for the given function. So condition number one, so we want f to be continuous on the given closed interval. So here's our a and here's our b. Well, this function here, f of x, is continuous as long as x is not equal to 1, because the top piece is a continuous polynomial, bottom piece as well, but this is a rational function. We must avoid x's making the bottom 0, and that's x equals 1. And if you're considering any interval not containing 1, we should be safe. In fact, the interval provided to us is 5 halves and 4, and 1 is not there, so we're safe to call that f as continuous. Number two, we want f attain different values at the endpoints of the interval. Go ahead and have your calculator ready and evaluate f of 5 halves and f of 4. All right, I have 35 over 6 and 20 over 3. And the good news is that these guys are not equal, right? So these guys are not equal, right? This value is not the same as this value, okay? So condition number 3, right? So we have f of c equals a, so k equals 6. So let me just write it here. K is equal to 6, and we want this k to be in between these two values. And in fact, 35 over 6 is less than 6, and this is less than 20 over 3. So as you see, all three conditions of the theorem are satisfied. Okay, and what is the conclusion here? So the conclusion says that there exists at least one number c. We don't know exactly what that number c, but we know that that c is in between a and b, such that f of c attains the value of k. So we know that, going back to the statement here, that f attains the value of 6. So there's a c, one or maybe more than one c, such that f of c equals 6. So let's go ahead and try to come up with c. All right, we know the description of the function that is provided in the statement of the problem. So x squared plus x divided by x minus 1. So we want f of c to be 6. So then c squared plus c divided by c minus 1 equals 6. Let's just use a little algebra. Let's multiply both sides by c minus 1. So c squared plus c equals 6c minus 6. All right, we can factor this out as c minus 2, c minus 3, or you can go ahead and use the quadratic formula if you wish. So we have two solutions. One is c equals 2, and the other one is c equals 3. So now the question is like, which one or which ones, like are those two of them the right answers, or maybe just one of them. So, well, to check that, we look at our interval. Our interval is 5004. Only 3 belongs to that interval, and c equals 2 does not. Even though the function attains the value of 6 at 2, the interval that we're considering is 5004, so only c equals 3 is in that interval. So the guaranteed c in the description of in the statement of the intermediate value theorem is only 3 in our case. So 3 is the answer. All right, so we applied the intermediate value theorem to a given function on the given closed interval, and we came up with the answer by solving an equation. But here the catch is that before you apply the intermediate value theorem, you have to check all 3 conditions, number 1, number 2, and number 3, before you apply the intermediate value theorem. All right. So this is the end of the video. Thanks for watching. I'll see you in another video. Bye.